Gonna have a quick look at radioactive half-life. The picture you see is of the nuclear power plant in Chernobyl. It's in the northern Ukraine, and in 1986 there was a bit of a meltdown. Not a nuclear explosion as such, but a massive increase in temperature and pressure. And it blew the nuclear containment facility and scattered radiation all over the surrounding area. It was so dangerous, in fact, and the half-life of the materials is so long that it won't be safe for humans to live in for another 20,000 years, which is crazy. So, first of all, what is half-life? Half-life is a period of time. Sometimes you can see it drawn in textbooks as T half, like so. And it's the amount of time it takes for the number of nuclei in a sample to half. So if you start off with 4 billion nuclei of uranium, it'd be the amount of time it takes to go to 2 billion. So in this little animation here, you can see the radioactive decay flipping nuclei from red to blue. So I think it's about to restart here, and you should see it go from blue, and it'd be the amount of time, about now, it takes to half, which that was roughly 2 seconds. It took for the blue nuclei, half of them, to turn to red. Next up is another definition, and it's the amount of time it takes for the activity or the count rate to half, which is kind of the same thing. So let's say this is giving off 3 billion alpha particles per second, or in radioactive terms, you'd say that as a count rate of 3 million becquerels. It'll be the amount of time it takes to go to 1.5 billion becquerels. So the activity, it's giving off half as many particles per second. Now the half-life graphs always look the same. On the bottom, you'll have time, and it could be in days, seconds, weeks, minutes, whatever it may be. It depends on how unstable the isotope is. In this case, we're looking at the activity, or the count rate per minute, and it starts off at 80. Now, half of 80 is obviously 40, and the amount of time it took to half, so if we read off the graph here, if we go down here, we've gone 2 seconds. Now, it took 2 seconds to half from 80 to 40. If we look at any other half value as well, we can go from 40 to 20, and it should be the same amount of time. So between 2 and 4 there, that's another 2 seconds. Between 20 and 10, it should also be another 2 seconds between 4 and 6. So it's the amount of time it takes for whatever is on the y-axis essentially to half. So here's another graph. This is a bit of an unusual one because we're looking at percentage. Makes things really easy, I suppose. Half of 100% is 50%. The amount of time that took was 5,700 years. Here's another one. We've got activity or count rate here again. And we've got time in seconds. So what do you think the half-life of nitrogen-16 is based on this graph? So we're starting off just above 6,000 here, so it looks about 6,400 perhaps. And the amount of time it takes to half to go to 3,100 would be about here. Okay, so the amount of time it takes to half be roughly there. Now, if we're looking at time in seconds, there's no way it's going to be 4. It's definitely not 60, that's the entire graph. It's not 30, that's half the graph. Well, that could be misconstrued as being the definition of half-life. Answer number 1, 7 seconds. Here's another one. How would it take, to what value would the count rate of nitrogen-16 have fallen after 4 half-lives? So before we established that it was 7 seconds. Okay, so after 4 half-lives, if it began here at 6,400, what would the count rate be after 4 half-lives? So let's have a look. There are mathematical methods of doing this, but you can just figure it out this way. So here's 1 half-life. I'll go 3,200. After another half-life, that'll be 2 half-lives, so it'll go to 1,600. After a third half-life, it'll go to 800. And after one more half-life, that'll be 4 half-lives, it'll go to 400 counts per minute. So the correct answer is 4. This is a really tricky question. Uranium decays into lead given enough time. And the half-life of uranium is 4 billion years. Now a sample of radioactive rock contains 7 times as much lead as it does uranium. You've got to figure out the age of the sample. So if you want to try and figure this out, pause the video. And if you just want to hear me talk nonsense or try and give you some help, calculate the age of the sample. So if we got 7 times as much lead as uranium, that means we originally, well, we've got 7 out of 8 parts. So original sample of uranium was 8/8, so that's 100% uranium. After one half-life, it will have decayed to 4/8, so half of 8. After another half-life, we'll have gone to 2/8, or 1/4 of the original sample of uranium. And after another half-life, we've got our magic ratio. So 1/8 of uranium remains, or 7/8 is now lead. So how many half-lives was that? That was 1, 2, 3 half-lives. So therefore, 3 half-lives will be 3 times 4 billion years, which is 12 billion years.